Welcome to The Explainer. Today, we're diving under the hood of electric vehicles to find the real brains behind all that brawn.
You know that feeling, right? That instant, thrilling acceleration you get when you put your foot down in an EV? It's amazing. But here's the thing. The secret isn't just in the battery or the motor. Nope. It's actually in the unsung hero that controls the whole show.
Yeah, we hear all the time about battery range and motor power, but the real magic, it happens in a component that most of us probably don't even think about. It's called the motor control unit, or MCU for short.
Okay, think of it like this. If the battery is the heart and the motor is the muscle, then the MCU, well, it's the brain. It is the sophisticated command center for the entire powertrain, managing every single watt of power. And that influences everything: performance, efficiency, and, yeah, even safety.
All right, so let's get into it. What does this thing actually do? What's really going on inside that little box?
Well, at its core, the MCU is basically a master translator and regulator. See, the battery puts out raw direct current, that's DC power, but the motor needs a very specific kind of alternating current, or AC power, to work. So the MCU takes that DC power and transforms it into exactly the right kind of AC power the motor needs to get you moving.
And you can see its central role right here. It sits smack dab between the battery pack and the motor. It's taking in all these inputs from you on the accelerator pedal, from the car's other systems, and it uses all that information to deliver a perfectly controlled stream of power. It's kind of like the ultimate middle manager, making sure everything works together in perfect harmony.
So, it's basically juggling three main jobs all the time. First, like we just said, there's power conversion. That's a big one. Second, it's managing torque. That means it's adjusting the power thousands of times per second based on how hard you're pushing that accelerator. And third, it does this really cool trick called regenerative braking. This is where it completely reverses the flow of power to actually send energy back into the battery when you slow down. Pretty neat, huh?
Now, this might sound straightforward, but trust me, it is not simple. We are talking about taming an immense flow of power here, hundreds of kilowatts of electricity. To put that in perspective, that's enough juice to power dozens of homes. And the MCU has to control all of it with absolute precision, instantly. It is a truly massive engineering challenge.
And all that real-time decision-making? That's what gives an EV its personality, its character. It's the difference between a ride that's smooth and responsive and one that's jerky and inefficient. When they get this right, the car feels like it's reading your mind. But if they get it wrong, whoa, you could actually damage the entire powertrain.
So how do engineers solve this super complex control problem? Well, they've basically come up with two main approaches. You could almost call them two different philosophies. They're called field-oriented control and direct torque control. And they're just two different ways of tackling the exact same challenge. Let's break them down. You've got field-oriented control, or FOC. Think of this one as the precise planner. It's meticulously calculating every move in advance for super smooth, efficient control. Then you have direct torque control, or DTC. This one is the quick reactor. It doesn't plan as much, it just makes instantaneous adjustments on the fly, which makes it incredibly fast.
And this really shows you the trade-offs engineers have to make. DTC is quicker and more robust, meaning it's not as picky about the motor's exact parameters. FOC, on the other hand, is a bit more complex, a bit more sensitive, but it gives you this excellent, really refined performance across all sorts of speeds.
So, at the end of the day, it's not like one is universally better than the other. They're just different paths to the exact same destination, perfectly and effectively managing the motor's power, no matter what the conditions are. Okay, so why should you care about any of this? I mean, these are super complex algorithms, right? Well, it turns out that this one engineering choice has a huge impact on how the car actually feels to drive every single day. Seriously, this single decision affects, well, pretty much everything. It impacts that feeling of instant acceleration and smooth braking. It affects how efficient the car is, which of course changes your vehicle's range. It even has an effect on the car's price and its long-term reliability. It's a really big deal. And because the stakes are so high, engineers don't just guess. They use these incredibly complex simulation systems to test and validate every possible scenario. I mean, they can test everything from slamming on the brakes on a sheet of ice to climbing a super steep mountain, all to make sure the controller's software is absolutely flawless before it ever gets into a real car. Which kind of leaves us with this one last fascinating thought. As cars get smarter, more connected, and eventually fully autonomous, is the controller's brain going to become even more important than the motor's brawn? You have to wonder. When the car is driving itself, the intelligence making the decisions might just become the most critical part of the entire vehicle. The brains, truly, over the brawn.